Hi, I'm going to talk about our paper, double block length hash function for minimum memory size. I'm Yu Kenaito, and this is the joint work with Yu Sasaki and Takeshi Sugawara. This is a summary of our results. Our goal is to provide block cipher-based or single block cipher-based double block length hash functions with minimum memory size. The memory size determines the overall hardware cost in lightweight implementation, and existing double block length schemes do not achieve the minimum memory size. So we propose new double block length hashing modes, XXNI and XXI, that have the minimum memory size. Regarding security, XXNI achieves optimal indifferentiable security and XXI achieves optimal collision security. And we compare hardware performances of our hashing scheme and the existing double block length hash function Romulus H, which is a finalist of the ongoing NIST lightweight cryptography standardization process. As a result, our scheme reduces 30% of hardware cost. Okay, so firstly, I explain the background of our research. Lightweight cryptography has been a topic in cryptography for more than a decade. The motivation is to design cryptographic algorithms that achieve efficient performances by design to provide data security for resource-constrained devices. Lightweight includes a lot of meanings such as small memory size, power consumption, latency, and so on. And the target of this talk is memory size. Memory size determines the overall hardware cost in lightweight implementation. So by reducing our memory size, the hardware cost is reduced. And in lightweight cryptography, sharing a printing for multiple functionalities is important because thanks to the common primitive, one can reduce the total memory size. In the ongoing NIST lightweight cryptography standardization process, authenticated encryption and hash functions are considered, and now 4 out of 10 finalists support both authenticated encryption and hash function. NIST selected different types of printing due to design diversity. Design of hash functions is the topic of this talk. A hash function takes an arbitrary length input string and returns a fixed length string such as these bit lengths. Hash functions are designed so that these security notions are satisfied and designed by using these primitives: block cipher, Tika block cipher, and permutation. In the NIST standardization process, 4 finalists support hash function, and 3 finalists are permutation-based schemes, and the other is the Tika block cipher-based scheme. And this talk focuses on block cipher and Tika block cipher-based construction. So block cipher is a family of permutations indexed by keys, and block cipher is mainly used as a components of symmetric key algorithms, such as authenticated encryption and message authentication code. And in these settings, a block cipher key is random and secret. So when designing a block cipher-based hash function, the input and the output become public. So using the decryption function of the block cipher, the primitive security is easily broken. That is given the output Z, then using the decryption function, one can easily find the input X and M. So to avoid such attacks using the decryption function, the input is feed forward to the output like this figure. This is a Davis-Meyer mode. And the feed-forward operations ensure collision result up to 2 to half of n carry complexity in the ideal cipher model. N is the block size. And then variable input length hash function can be obtained by combining a compression function with the domain extender such as Mach-Dangard. This is a Mach-Dangard with Davis-Mayer mode. On the other hand, the output lengths of block ciphers are commonly less than or equal to 128 bits, such as the AES and Skinny, but the output lengths of block ciphers are too short. So when using the 128-bit block cipher, the security is ensured up to only 2 to 64 carry complexity due to the birthday attack. So hash functions such as SHA-2 and SHA-3 are designed so that the output lengths are greater than or equal to 224. So double block length design is a useful approach to solve the problem where the out length is extended by calling a block cipher twice. So this figure is one of the double block length schemes, Hirose schemes, where a block cipher is called the upper and lower part, and so the out length becomes the 2n bit. And so far, several double block length schemes have been proposed, such as Hirose scheme, Tandem DM, RSDM, and so on. And these schemes achieve collision resistance up to 2n carry complexity, which is optimal collision security for 2n bit output length. And then variable input length double block length hash function can be obtained by combining double block length schemes with domain extenders such as Mach-Dangard. Regarding memory size of double block length hash functions, due to the input length of the underlying block cipher, the minimum size is at least n plus k bits. N is the block size and k is the key size. On the other hand, existing double block length hash functions need at least 2n plus k bit memory. And existing double block length hash functions are mainly categorized into these two types. The first type uses a feed-forward operation like this figure. This type needs memory to keep one output block of n bits while calculating the other n bit output block. So for example, this double block length scheme performs the upper and lower part parallel. So this double block length scheme keeps this n-bit output block when calculating the upper part. The upper part requires 2n plus k bit memory. On the other hand, the other type, this type does not use feed-forward operation. Although the feed-forward operation is used to avoid attacks using a degradation function, Uzen's sum shows that by iterating the double block length scheme, like this figure, the resultant scheme becomes an optimal collision resistant hash function. So by removing the feed-forward operation, the memory size is improved to 2n plus k bits. This figure summarizes existing double block length schemes. This line shows the memory size. As you can see, none of existing schemes do not achieve the memory size n plus k bit. So we solve the open problem. We first explain a basic component of our double block length hash functions, XX. This figure shows the XX structure. Idea behind our scheme are that a 2n-bit internal state is updated by sequentially processing the block cipher, and our memory for the underlying block cipher is commonly used to keep the internal state. As a result, XX achieves the minimum memory size. Note that although these key inputs must be required to calculate the next internal state values, but key input can be recovered by inversing the key schedule of the underlying block cipher. So this scheme does not require a memory to keep these key inputs. For security, we design an XX-based hash function so that these requirements are satisfied. These are the requirements of this standardization process. However, XX itself is not a secure function because one can easily calculate a preimage from the output or by using a degradation function of the block cipher. So we use the idea by using some, that is, we ensure these requirements by iterating the XX scheme. This is the main construction of our result, XXNI. XXNI is designed so that it is indifferentiable secure, which ensures security against the length extension attack, as well as collision resistance. Regarding the structure, XXNI has the iterative structure of XXNI scheme, but iterative hash function is vulnerable to a length extension attack, which breaks the indifferentiability. So to avoid the length extension attack, we make use of the nested structure in this part. By the iterated nested structure, we can ensure that XXNY is indifferentiable secure up to this security level. So when using 128-bit block cipher, XXNY achieves indifferentiable security up to this security level, which satisfies the requirement of our goal. The next scheme is XXI. The motivation of designing XXI is to improve the efficiency of XXNI. Since several applications do not require security against length extension attack, we can remove the nested part, which is introduced to resist the length extension attack. So by iterating the XX function like this figure, we can ensure collision security up to this security level. Since the nested part is removed, XXI is faster than XXNI by 2 block cipher calls. So far, I explained our hash functions using this XX function, but the security holds even when inserting linear functions pi1 and pi2 in this part. Motivation of the modification is to remove the inverse of the key schedule. So if the key schedule of the underlying block cipher is linear, then by setting the key schedule to these linear operations, we can reuse the results of the key schedule to update the internal state, thereby saving the cost of the inverse of the key schedule. This slide compares our double block length hash functions with existing scheme. As shown in this line, the memory sizes of our hash functions are smaller than the existing scheme. This slide shows hardware performance evaluations of our hash functions. We compare our hash functions with Romulus H, which is finalist of NIST standardization process. Romulus H is a combination of MDP-H mode and skinny. So we use the same primitive for our hash functions, and we implemented these schemes with the same design policy. Since the memory sizes of our modes are smaller than MDP-H mode by 20 bits, our hash function reduces 30% of hardware cost. This is the conclusion of my talk. We propose 2 double block length hash functions, XXNI, XXI, that achieve minimum memory size and optimal security. XXNI is indifferentiable secure up to this security level, and XXI is collision resistant up to this security level. So when using 128-bit block cipher such as skinny, XXNY and XXI satisfy this security level, which is required by NIST standardization process. We finally compared our hash functions with Romulus H, and our hash function reduces 30% of hardware cost. This is end of my talk. Thank you very much.